So this is just a brief recap of differentiation. Differentiation is just a basic set of rules. You learn the rules and everything else will just flow from there. So our rules start with what do we get when we differentiate certain things. So I'm just going to say that I have a and n, and they're just numerical constants. So if y is equal to a, just a constant, when I differentiate a constant, if I think about my differentiation being the gradient of my line, if I differentiate a constant, so this is y and this is x, then my gradient is 0, and so I differentiate a constant, and I get 0. If I differentiate x, this would be this case here, sorry, it's not quite going through 0, what I find is that I get 1, and the reason this is because I have a rule. My rule is that x to the n, when I differentiate it, goes to nx to the n minus 1. It doesn't matter whether n is an integer, it could be a fraction, it could be negative. This is always my rule. The only case it doesn't work is when it's x to the 0, because x to the 0 is a constant, and so my constant follows this rule here. So I can take this a little bit further and have x to the n going to nx to the n minus 1. And if I have a polynomial, so if I have something like 2x squared plus 4x plus 7, what I find is that I just need to take these each in turn. So in this case, dy by dx is equal to, differentiate this one, so this is going to be 2 times 2x to the 2 minus 1 plus differentiate this one, 4 times 1, x to the 0 plus 0. So if I just tidy this up, this becomes 4x plus 4. So any polynomial just follows that rule. So now, what happens if I have things other than polynomials? Well, if I have e to the x, that is essentially, can be given to me by this expansion. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... And if I work that out, what I actually find out is when I differentiate e to the x, I end up with e to the x. If I have e to the ax, when I differentiate it, I'm going to end up with ae to the ax. And I can take this a little bit further, if it was a minus sign, so if I had e to the minus x, that's the same as me having a is equal to minus 1. And so this becomes, when I differentiate it, minus e to the minus x. Yeah? I don't lose any of my integer power here, it always remains the same. I also have what happens if I have sines and cosines and things like that. So I'm going to just write this kind of loop. And here, if I'm differentiating things, I'm going to go around this clockwise. So that's my differentiation. What we'll find when we do integration is I'm just going to go the opposite way. So sine becomes cos becomes minus sine, and minus sine becomes minus cos. So I can write those into my table here. So sine x becomes cos x, and cos x becomes minus sine x. And I can actually take this a little bit further, because if I actually have the sine of ax, that is going to become just the same kind of example as I had with e to the x and e to the ax. This becomes a sine ax. So the sine of ax becomes a sine. Oh, sorry, I've got those both wrong, sorry. Cos ax. A cos ax. Sorry about that. So there's basically only one more function that I've said that you need to be able to differentiate, and that's the log of x. And in this case, this is just one that you're going to have to learn. This becomes 1 over x, which is the same as x to the minus 1. If I have something like the log of 8x, this doesn't become 1 over 8x, because I can say that the log of 8x is the log of 8 plus the log of x, just from my rules of logs. If I differentiate the log of 8 is just a constant. So when I differentiate this, I end up with just 1 over x regardless.